This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we'll be delving into a research paper exploring the use of world models in model-based reinforcement learning, MBRL, for anomaly detection during inference. The authors propose a method to enhance the safety and reliability of learning-based controllers by continuously monitoring discrepancies between a world model's predictions and observed system behavior. What are your initial thoughts on this approach, given its potential implications for real-world robotic applications?
The core idea leveraging a trained world model for real-time anomaly detection is quite compelling. It addresses a critical limitation of many learning-based controllers, their unpredictable behavior in unfamiliar situations. By continuously comparing predicted and actual system states, the method offers a universal safety mechanism independent of the specific task. However, the effectiveness hinges on the fidelity of the world model and the robustness of the error metrics used for anomaly detection. The paper's claim of universal applicability needs careful scrutiny, as the performance might vary significantly depending on the complexity of the environment and the quality of the training data.
The paper mentions Dreamer v3, a state-of-the-art MBRL algorithm. How does the choice of Dreamer v3 influence the proposed anomaly detection method, and what are the advantages and limitations of using this specific algorithm?
Dreamer v3's architecture, particularly its autoencoder-based world model, is crucial. The autoencoder's ability to compress observations into a latent space allows for efficient prediction, but its inherent limitation of poor generalization outside the training distribution becomes a double-edged sword. While this poor generalization can signal anomalies, it also means the system might flag false positives if the real-world scenario deviates slightly from the training data. The simultaneous training of the world model and policy in Dreamer v3 is advantageous, ensuring consistency between the model's predictions and the policy's actions. However, the reliance on a single algorithm limits the generalizability of the findings.
The paper highlights both simulated and real-world experiments. How do the results from these different environments compare, and what insights do they offer regarding the practical applicability of the proposed method?
The simulated experiments, using the DeepMind control suite, effectively demonstrate the concept. They showcase the ability to detect both global, e.g., changes in gravity, and local, e.g., actuator defects, anomalies through increased prediction errors. The real-world experiments with a quadcopter further validate the approach, showing anomaly detection in response to unexpected external forces. However, the real-world results highlight the challenges of Sim2 real transfer. Discrepancies between the simulated and real-world environments, such as differences in the drone's climb rate, affect the accuracy of the predictions and the interpretation of the error signals.
The paper discusses the use of observation and reward errors as metrics for anomaly detection. What are the strengths and weaknesses of these metrics, and are there alternative or complementary metrics that could improve the performance of the anomaly detection system?
The average absolute difference used for observation and reward errors is simple to implement but might lack sensitivity to subtle anomalies or be overly sensitive to noise. For image-based observations, the paper suggests using pixel-wise differences, which is rudimentary. More sophisticated image comparison metrics, such as structural similarity index, SSIM, or perceptual loss functions, could provide more robust and informative error signals. Furthermore, incorporating other metrics, such as prediction uncertainty or entropy, could enhance the system's ability to distinguish between true anomalies and noise.
The authors acknowledge that a prediction error alone doesn't provide insights into the underlying cause of the anomaly. How can this limitation be addressed, and what strategies could be employed to improve the interpretability of the anomaly detection system?
The lack of interpretability is a significant limitation. Task-specific knowledge is crucial for interpreting the meaning and significance of prediction errors. Weighting errors based on the importance of different state variables is one approach. Another is to feed the prediction errors back into the agent's learning process, allowing it to learn how to react appropriately to different types of anomalies. This requires more sophisticated reinforcement learning techniques and potentially more complex reward functions.
The paper suggests that the proposed method could aid in Sim2 real transfer and improve the interpretability of neural controllers. Can you elaborate on these potential benefits and discuss their implications for the development of more robust and reliable robotic systems?
During Sim2 real transfer, the method acts as a powerful debugging tool. Discrepancies between simulated and real-world behavior are readily apparent through prediction errors, allowing for quick identification and correction of implementation issues or model mismatches. This improved debugging process also contributes to a better understanding of the agent's behavior, leading to more interpretable neural controllers. This enhanced interpretability is crucial for building trust in autonomous systems and ensuring their safe deployment in real-world scenarios.
The paper concludes by suggesting that the ability to detect and investigate inaccuracies in the agent's understanding of the world could eventually enable self-correction and improvement. How realistic is this long-term vision, and what are the key challenges that need to be addressed to achieve this level of autonomy?
The vision of self-correcting and self-improving agents is ambitious but not unrealistic. The ability to detect anomalies is a crucial first step. However, the ability to interpret these anomalies, understand their causes, and develop appropriate corrective actions requires significant advancements in AI research. This includes developing more robust and generalizable world models, more sophisticated reinforcement learning algorithms, and more effective methods for knowledge representation and reasoning. Furthermore, ensuring the safety and reliability of such self-improving systems is paramount and requires careful consideration of ethical and societal implications.
The paper references several related works in MBRL and anomaly detection. How does this research build upon and extend the existing literature, and what are the key contributions that distinguish it from previous approaches?
The paper builds upon previous work in MBRL by focusing on the use of world models during inference rather than just during training. It extends the application of violation of expectation frameworks from developmental psychology to the domain of robotic control. The key contribution is the demonstration of a universal safety mechanism for learning-based controllers, applicable to both simulated and real-world environments. The use of Dreamer v3, a state-of-the-art MBRL algorithm, and the comprehensive evaluation across various tasks and environments further strengthens the paper's contribution.
The paper mentions the potential for combining visual and numeric observation spaces to improve world model fidelity. What are the specific advantages of such a multimodal approach, and what are the technical challenges involved in integrating different data modalities?
A multimodal approach offers richer and more complete information about the environment, leading to more accurate and robust world models. Visual information provides spatial context and object recognition capabilities, while numeric data offers precise measurements of system states. Combining these modalities can improve the system's ability to detect anomalies, especially those that might not be readily apparent from a single modality. The technical challenges include designing appropriate architectures for processing and integrating different data types, handling potential inconsistencies between modalities, and managing the increased computational complexity.
The discussion of global versus local modifications in the environment is insightful. How does the nature of the anomaly, global versus local, affect the pattern of prediction errors, and how can this information be used to improve the diagnostic capabilities of the system?
Global modifications tend to produce widespread, albeit small, prediction errors across many state variables. Local modifications, on the other hand, result in more focused and isolated errors, primarily affecting variables directly related to the modification. This difference in error patterns can be exploited to improve diagnostics. By analyzing the spatial and temporal distribution of prediction errors, the system can potentially pinpoint the location and nature of the anomaly more accurately. This requires more sophisticated error analysis techniques, potentially incorporating machine learning methods for pattern recognition.
The paper emphasizes the importance of considering task-specific knowledge for interpreting prediction errors. How can this knowledge be incorporated into the anomaly detection system, and what are the trade-offs between generality and task specificity?
Task-specific knowledge can be incorporated through various methods, including weighted error metrics, rule-based systems, or learned models that map prediction errors to specific anomaly types. The trade-off between generality and task specificity is crucial. A highly task-specific system might be very accurate for a particular task, but not generalizable to other tasks. A more general system might be less accurate, but more widely applicable. The optimal balance depends on the specific application and the desired level of accuracy and generality.
The paper briefly touches upon the potential for using prediction errors to train the agent to react appropriately to anomalies. What are the technical challenges involved in such a closed-loop approach, and what are the potential benefits and limitations?
A closed-loop approach, where prediction errors are used to train the agent's response to anomalies, presents several challenges. It requires careful design of the reward function to incentivize appropriate responses while avoiding unintended consequences. It also necessitates robust methods for handling uncertainty and noise in the prediction errors. The potential benefits include improved robustness and adaptability to unforeseen situations. However, the limitations include the potential for overfitting to specific anomaly types and the difficulty in ensuring the safety and reliability of the learned responses.
In summary, this paper presents a promising approach to enhancing the safety and reliability of learning-based controllers in robotics. While challenges remain in terms of interpretability, generalizability, and robustness, the proposed method offers a valuable contribution to the field. Thank you for this insightful discussion.